All right, week 7B. So here we're going to go through using substitution, which is just chain rule for integrating, and start talking about approximating the area under a curve. Okay. Substitution or chain rule. So the use sub technique is used to undo the chain rule. So for example, we have this integral of 2x cubed plus 1 to the fourth times 6x squared dx. So if we let u be 2x cubed plus 1, like our inside function, from the chain rule, then if I take its derivative with respect to x, I have du dx is equal to 6x squared. And then I rearrange it and I get du is 6x squared dx. Now I can substitute u for 2x cubed plus 1 and du for 6x squared dx, and we have this integral now instead. And here we're just highlighting in red and blue, and now I switch it out. Doing this takes a complicated integral and turns it into a simple one. So makes it easy to solve. Because I can take that integral of u to the fourth du, and we know how to solve that already, which is just u to the fifth over 5 plus c. And then we just back substitute. We had u equal to 2x cubed plus 1, plug it back in, final answer, right? And we can do a sanity check by just taking the derivative of the equation we got. And as long as we get the same thing, then we know we did it right. You can use this for any integration or differentiation. You just do the other one to go back to what you started, and that helps you double check your work. So we're going to run through an example here again. We're going to find the integral of this 6x times 3x squared plus 4 to the 7th. And here again, you can see we're going to need that chain rule. So we let u be the stuff in the parentheses, 3x squared plus 4, and then I get du is 6x dx. So now I'm going to switch everything out, and I just get that integral of u to the 7th du. And then we know that's just u to the 8th over 8 plus c, and plug back in our u. We have our final answer here. And we're going to roll with another one. Here we don't have the parentheses. I have a square root bar, but it's the same idea. We're going to use that underneath. But there's two ways to solve this, and you'll see why. So when we're looking for it, anything raised to a power, of course, is a good choice. So we pick our u to be x cubed plus 1. But then you see here that our du is 3x squared dx. I don't have a 3 in the original integrand, so I have to somehow compensate for that. One way is knowing that 1 is the same as 3 over 3. So I can rewrite that by putting 1 over 3 on the outside and 3 on the inside. Then, now I get my 3x squared dx that I wanted, right? That's going to be my du. So now we can substitute the u and du in, and I get 1/3 integral of u to the 1/2. So this is just two ways on how to deal with this constant that pops out from your du when I don't have it in the original. So this is one way. Now we just find that integrand. It's u to the 3/2 over 3/2, right? Multiply it by a third. I don't need the third here because the third is just adding to this constant that we don't really care what it is, so it can just be c. And now I'm just going to, you flip this here, right? Opposite, you put the reciprocal and multiply, and you get 2/9. Plug back in our u, and then here you can see it just becomes 2/9 x cubed plus 1 to 3/2 plus c. So now that we have this here, that's one way to do it. Another way is eliminating the constant. Really what that is that right here I have du is 3x squared dx. What I'm going to do is I'm going to divide du by 3. So now I have x squared dx, which is exactly what we have in the original. And now I know I just need to sub in a 1/3 du to compensate. And that's same thing here. Substitute u for x cubed plus 1 and du over 3 for x squared dx. So here we have this du over 3, but that's just a 1/3 multiplying. So I can pull the 1/3 on the outside. And then you see this is exactly the same integrand we had for method 1. We just got it a different way. But both ways work, whichever one you like better. You can either solve the du so that what you have on the right is exactly what you need, or you can recognize that I can just multiply by that fraction, same top and bottom, and move it around. Both work. So when we're looking for what to substitute, there are some pretty typical areas to look. One is going to be under a root bar or raised to some power. Like if I have parentheses around something, raised to a power. Anything in a denominator is a good place to look, or the exponent on e. So if you see anything with parentheses, good chance your u is going to be inside those parentheses. Good place to look. And you'll always know if you got it right or not because you'll see that derivative inside. If you don't see the derivative, then you chose something wrong. You should be able to substitute u and du and get rid of all of the other variables. You shouldn't have any x's or t's or y's hanging out. It should be completely in terms of u. And then we just have to remember that sometimes we will have to reorganize things like we did in the last question to make it match properly. We can always rearrange with constants to do that. So we're going to go through another one here. Repetition makes it easy. So now we have a fraction, x plus 3 on top, and x squared plus 6x to the power of 2 dx. So here we're letting that quantity inside those parenthesis bars. That's going to be my u. So then du is this 2x plus 6 times dx, but I can pull out a 2. Once I pull out a 2, then we see that this x plus 3 dx matches exactly what we're looking for over here. I just have this extra 2. So I'm going to pull a 1/2 out. I'm going to stick a 2 on the top, and that gets me this, which matches this. So then I can sub that in. So I just get du on top and u squared on the bottom. And we can rewrite that as u to the negative 2. And notice that this works. Like we can keep doing this. Negative 2 gives me the product rule again. Now, if it's negative 1, that's something different, and we'll do one of those. So here I replug in u for this yellow x squared plus 6. So I'm just plugging that u back in. And that's your final answer. So here, this is where we're going to look at, instead of using the power rule to undo a u sub, we're using either ln or e. So here, we have the integral of 2x minus 3 over x squared minus 3x dx. So our u is going to be this denominator, right? That's u. And then du, we take that derivative, and we get 2x minus 3 dx, which is exactly that numerator in our dx. So when I sub this in, though, I get du over u. And you got to remember that the integral of 1 over u is ln u. So this is why that -1 exponent here, that doesn't give me the power rule. That gives me ln. And it's ln with an absolute value bar, okay? Because ln can never have negative. I can't take the ln of a negative number. It's not allowed. So because I can't take the ln of a negative number, you need to put those absolute value bars on there, okay? I gave a buy to on the exam if somebody didn't use absolutes, if they use parentheses, but you guys need to use absolute value bars, okay? So then here we just plug in our u again, just inside those absolute value bars. So now let's do one with e. Now we know that the integral of e to the x is e to the x, right? Because that's the same for the derivative. But here we're going to use that chain rule because I have e to the x cubed. So x cubed is our u. And then when I take that derivative, I get this 3x squared dx. And again, notice that I have an x squared. I don't have a 3. So we need to pull out a 1/3 to give me this 3. And then I can substitute in my du right here. So we have 1/3, the integral of e to the u du. E to the u is just e to the u. And then we just plug back in our yellow x cubed right here. We have a final answer. And remember, again, we don't need that 1/3 on the c, right? Because c is just some constant. It doesn't matter what it is. Every type of constant being added just gets thrown into that c. Throw it all into the c. So if you do enough of these, you'll see a pattern, right? There are different forms that are integrated using u. And so one of them that we see a lot is this power rule, right? Looks a lot like our chain rule derivative definition for power rule. I have some function to the power of n times its derivative. Well, that lets me know I'm going to use the integral of u to the n du, u to the n plus 1, n plus 1 plus c. And I plug f of x in. So here you can see that the u is our f of x, and then our du is f prime dx. And then here we have f prime over f, and this over f, that's to the first power. So then when I do this blue, again, that's my du, and then my u is the yellow, it's that f of x, and that gives me ln of f of x, right? color everything in the yellow. And then here we have e to the f of x times f prime of x. So my yellow is f of x, which is my u. And then f prime of x dx, that's my du. As you can see, f of x is always our u, and f prime of x dx is always our du. You can kind of see a pattern. And if you notice the pattern, you're good. You don't have to follow every tiny step for substitution. As long as you know where you're going, you can start to kind of skip pieces, but make sure that you know where you're going. Double check it to make sure it works. Sometimes skipping too many steps because you're doing it in your head can cause you to have problems. So just be careful with it. Now here's an example that's going to be applied for a demand function. So the research department for our hardware chain determines that at one store, the marginal price of X boxes per week of a particular type of nails is this derivative function. So it's p prime of x. And that's negative 4,000 over 2x plus 15 cubed. Now, we want to find the demand equation from our marginal price, right? If weekly demand for this type of nails is 10 boxes when the price is $4. So I've been given the derivative. I have the marginal price here. And I want to find the demand equation. And then I'm also given initial conditions, 10 and 4. 10 boxes for $4. So using that, we're going to be able to solve for whatever our constant is at the end. So first, we have to find the demand function, which is just the integral of p prime. So plug it in. We're taking that integral. So now I'm going to let u be 2x plus 15 and du be 2 dx. So here's our original p of x prop equation here, our demand function. And now I'm rearranging it a smidgen so that way I can do this. Because du is 2 dx, you can see here I have a 2. I have a 2 here. I'm pulling out the 1 over 2, and I'm keeping the 2 dx to help me do my substitution here. So simplify that, and I get negative 2,000, plug in my u, and I get u to the negative 3 du. So here's my u, and my u, and my u, right? And now we just use power rule. So that's u to the negative 2 over negative 2 plus c. And then you can simplify that again. Negative 2,000 divided by negative 2. That just gives me 1,000. Move my u to the negative 2 into the bottom. So that's simplified out. And then plug back in 2x plus 15. So now I have my demand function. That part's done. But now I want the full thing with our initial conditions, right? 10 boxes for $4. So we know that when p is 4, p is equal to 4 when x is 10. Okay? So if I plug in p of 10, being in 10 for x, then I get 1,000 divided by 2 times 10 plus 15. And I know that that is equal to 4, because that's what it was told to me in the problem statement. So now we're just going to simplify it out. I get 1,000 over 35 squared, which is approximately 0.82. So that gives me C approximately 3.18. And the reason why we have 2 decimal places is because the demand function is also the price function. So what I'm finding is a dollar amount. Dollar amounts are done with 2 decimal places. So that's why we approximate it. So then we just plug in 3.18 for C, and we have our official demand function, our price function. 1000 over 2x plus 15 squared plus 3.18. So that's an applied problem to the demand function there. That's really just U sub. We're just figuring out what function is my inside function. What did I decide to multiply by for the derivative? And then I can use that to go backwards. So chain rule for integrals is U sub. Cool. So that's all U sub stuff. Questions, let me know. The more we practice it, the easier it'll get. So the next piece we talk about is area and the definite integral. So we were doing indefinite, right? We learned how to do indefinite for power rule, for ln's, for E, and then also using the U sub to do the chain rule stuff. But those were indefinite because I didn't have any bounds. I didn't say from 0 to 5 or from -2 to 10. I just said of this function. So definite means on an interval. So the first thing we talk about is approximating area. So if I have this blue region here, which is bounded by the axes and by this function, the square root of 4 minus x squared. If I want to find out what this area is, this blue area, I can approximate it by drawing rectangles underneath it, right? So I can chop it up into rectangles and then find the area of those rectangles. And that's going to approximate my area. And I can choose the height of these rectangles either by the left endpoint, the right endpoint, or the midpoint. So first, we're going to approximate this blue area, the area under the curve, by using 2 rectangles, and I'm determining the height by the left endpoint. So that means that the first rectangle's left endpoint is right here. Use a different color. I can just erase the big one. So the first left endpoint is right there, which is f of 0 equal to 2. And then I'm going to take the left endpoint of the next rectangle right here, and that's f of 1. Because I'm doing 2 rectangles, they have to be the same width, okay? Otherwise, it kind of messes things up. So we do the same width. So each one has length 1. So then I take 1 times the height, f0, and that gives me this yellow area, right? So I get this rectangle. Length times width. And then to get the green one, I take 1, which is our width here, and then I need to multiply by the height. And this height is f of 1. So when I add these two together, it approximates this area. And you can see that the area that I'm getting is bigger than the area under this graph here, right? I'm getting more stuff than I would normally. So it's fair to say that this approximation is going to be too big. Now we can approximate the same thing, but instead I'm using the right endpoint. And notice when I pick the right endpoint for two rectangles, the first rectangle is f of 1, but the second rectangle is f of 2, and f of 2 is 0. So really, I'm only taking the area of this blue spot here, which is much less than the real area. So here you can see f of 1 and then f of 2. f of 2 is 0. f of 1 is square root of 3. So 1.7321 approximately, which obviously is very low, right? It's not a very good estimation, approximation. And here, again, that. So if we pick the midpoint instead, you can see that looks a bit better, right? We're overestimating a little bit here. We have a little bit extra here, but I am kind of making up for these two white gaps that I'm not measuring. So it's usually going to be more accurate if you use the midpoint. And that's called the midpoint rule. So here we're going to take the midpoint. So the center of our first rectangle is at 1/2. And the center of our second rectangle here is at 3/2. So now I'm taking 1 times f of 1/2 plus 1 times f of 3/2. And here we get approximately 3.2594, which, looks pretty good. But we can improve the accuracy of our approximations by increasing the number of rectangles. So now if I use 4 rectangles and left endpoints, I'm going to divide that interval into 4 equal parts. So then each piece is going to be 1/2. And then plugging in those left endpoints, my first left is 0, my second left is 1/2, my third left is 1, and my fourth left is 3/4, or 3/2. And so here we're just taking 1/2 times each of those points, adding them all up together, and that's going to give us an approximation of 3.4957. So we're getting closer. But we can again use 8 rectangles instead. Every time I add more rectangles, you can see that my approximation here is getting closer and closer to what it would actually be. So here, plugging everything in, each one has got a width of 1/4. I get approximately 3.3398. And we can keep going and keep going and keep going, right? The more rectangles I have, the better approximation. So here is a table letting you know if I use the left endpoints, the right endpoints, trapezoidal rule, which you guys don't really have to worry about, and midpoint. And N, that means how many rectangles am I using? And so here, as we use more rectangles, you can see that these numbers start to get really close to each other. 3.1455, 3.1375, 3.1415, 3.1416. So I'm starting here, you can see crazy differences. And as we go down, we can see that the numbers kind of coalesce to roughly the same number. So that's just adding to the fact if I have lots of rectangles, I get a better approximation. And here you can see on the graph having 10 rectangles versus having 20. And just immediately you can see we're getting a better approximation here. Now, what I want to do is I want to write a generic kind of thing here. So here we have x1 to xn. So that tells me I have n rectangles of equal width. This pink rectangle in the center here, that's called the ith rectangle. So its area is the product of length and width. What we're saying here is that this height is going to be f of xi, or xi, Ith just means it's some arbitrary x. It could be any of them. So I can pick an I and then plug in the answer, if that kind of makes sense. So its width is delta x. It means the change in x, right? If I make each width the same, then that change in x is the same for every single one. And then its height, f of xi. So then the area of this ith rectangle is f of xi times delta x. Okay? But the total area under the curve is approximating by summing the area of all of those n rectangles. Using sigma notation, which just means you're summing, this total area becomes the sum from I equals 1 to n of f of xi times delta x. Because what I'm saying is this is just any generic rectangle. I can pick any I, plug in that number, and this would be its area. Because every delta x is the same. All of my rectangles have the same width. So what's changing is the f of xi. Because as I move on the curve, that number is going to change. And this summation means I'm going to first plug in 1. So I have f of x1 times delta x. Now I'm going to add when I is 2. F of x2 times delta x plus, and on and on and on and on until I've done all n rectangles. So the exact area under the curve is defined to be the limit of this sum, as long as the limit exists. So I'm starting with my n rectangles, and I want to find the limit as n goes to infinity until I do as many infinite rectangles as possible. So we're going to take this summation, which is what we came up with, right? That's the area under the curve using n rectangles. And now I'm going to send this n to infinity. So I'm going to go until I have infinite rectangles. That gives me the exact area that's under the curve. And whenever this limit exists, it's defined, it's called the definite integral of f of x from a to b. Okay? So here, the definite integral of f is defined, if it's defined on the interval a to b, then the integral from a to b of the function dx is equal to this limit as n goes to infinity of the sum of all of those rectangles area. And this delta x is the interval b minus a divided by n, the number of rectangles. So that tells you what's my width got to be. If I take my whole interval, figure out how long it is, b minus a, divide it out by the number of rectangles, that's my width. And xi is any value of x in the ith interval. Sounds a bit scary, but we will do some examples and it should make some sense. So here, we're going to approximate the integral, the definite integral, from 0 to 4 of 2x dx, which is the area of the region under the graph of f of 2x. F is equal to 2x. And it's above the x-axis, and it's between 0 and 4, because that's what my interval is here. So that tells me what x value to start at, what x value to end at. Every definite integral is measuring the area from the curve to the x-axis. That's it. That's the ending point. Okay? So that's why we can use rectangles to do this, because it's just doing to the x-axis. So when we're solving this, we want to use 4 rectangles. So it tells us we want 4 rectangles, and I want to use the midpoint. That tells me what points am I going to pick for my heights. So the width is this delta x, which is our interval, 4 minus 0. I'm doing 4 rectangles, so divided by 4. And that tells me each interval, each width of my rectangle is 1. And then we can make a chart here. This tells us which xi's do I need, because I'm doing the midpoint. And then what is the value of that when I plug it in? So if I'm starting here at 0 and I'm going to 4 and I want the midpoint, then what I want to say is, okay, well, the midpoint between 0 and 1 is a half. So my first one is 0.5 because it's this dot here. And then the second one is 1.5. And then we have 2.5 and 3.5. Because I'm doing 4 rectangles, that's all I need. So making a chart makes it easy to have all the values you need that you're ready, because now we're going to put it into the whole summation line. So here we have our sum from I equals 1 to 4 of f of xi times delta x, which means f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. And now I'm plugging in my midpoints. Now I'm plugging in my values, and I solve. And it's 16. So this is what that summation notion really means, summation notation. It means plug in 1, cool. Plug in 2, add it. Plug in 3, add it. Plug in 4, add it. All the way down. This tells you where to start. This tells you where to end. Another thing that we can use for definite integrals is looking at total change. For example, if I have this function f of x squared plus 20, and this is the marginal cost function, right? So what that tells us is if f of 2 is 24, that means that the rate of change of the cost at x equals 2 is equal to 24. Or the unit change in x will produce a change of 24 units to the cost function. So that's just defining what does it mean for the marginal cost function, right? And I can do f of 3, if it's equal to 29, then each unit of change in x produces a change of 29 units in the cost function when x is 3. But if I take the definite integral of our cost function from 2 to 3, that tells me the net total change in the cost as x goes from 2 to 3, which is really useful. So if f of x gives us the rate of change of some antiderivative for x in this interval, then the total change, right, because I'm just adding up the change from each of these, that gives me our total change. So it's just saying that this limit of our rectangles is equal to this definite integral. And we're going to do an example here. So example, we're looking at oil leakage. So this figure below here is showing us the rate that oil is leaking from a machine in a large factory in cubic centimeters per hour, with specific rates over a 12-hour period. So over this 12-hour period, right, they're measuring it. And here is our chart labeled here. These are when x is 0, x is 1. So every hour, using the left endpoints, this is what the rate of leakage is. My y values is the rate of leakage. So using this table and this graph, we can approximate the total amount of leakage over a 12-hour shift. So how much oil has actually leaked out of this machine in 12 hours? And we can approximate that. So we're going to divide all of our rectangles equally. So we have 12 rectangles. Using each rectangle is one of those hours. So each subinterval has width 1 because it corresponds to 1 hour. And we're using the left endpoint because that's what we were given on our chart in our graph there. The table. So using those values from the table and multiplying each one of them by 1, I just add them all up, and that gives me my approximate total volume that was leaked out of that oil machine. And it was centimeters per hour, cubic centimeters per hour. Yep. So that's how many cc's of oil that leaked out, approximated. So approximately 187.8 cubic centimeters of oil leaked out during this time. Mathematically, right, because this is a definite integral, we're saying that the area, the definite integral 0 to 12 of f of x dx, approximately 187.8. Or the area under the curve of f of x, which was in the graph, that area under there is approximately 187.8. So a way to apply total change. Another one to look at is total distance. So a driver is traveling on a business trip. He's checking his speedometer every hour and kind of writing it down. Let me get this chart here. So at every hour here, he checks his speed at the beginning of the hour, right? So at time 0, he's going 0 miles an hour. At 1 hour on the dot, he's going 52, 2 hours, 58, and 3 hours, 60. So we want to approximate the total distance traveled during the 3-hour period using the left endpoint and then also using the right. So if I use the left endpoint, I want 0 and I want 52 and I want 58 because I'm using the left side. That gets me 110. If I use the right endpoints, now I want 52, 58, and 60 because I'm using the right side. But just like we've seen before, the left endpoints is too small and the right endpoints are too big. Because when we look at it under the graph, you can see where that space is not being covered or being overcovered. So instead, if I take the average of the two, 140 miles, it's going to be a better estimate of the total distance traveled because I'm averaging the two out. So that is the end of 7B. So you have your last quiz this week. Exciting. And then next week we have one homework assignment, which is 8A. And then we'll have an exam next Friday. And then that's it. You guys are done. Hopefully get to enjoy the rest of your summer. I will be doing a review session next Thursday from 5 to 7. For anyone who'd like to stop by, we'll go over the practice exam. And I'll post the practice exam this week on Friday. You guys have the end of the weekend and next week to study and practice up. So it'll just be from implicit differentiation through the area between two curves. All right, well, I will see you guys in the next lecture.